So this is part 2 of the Aldol reaction, and we haven't actually gotten to the actual Aldol reaction. I kind of want to make that point clear here. We're building up to it, and we're discussing some things with enols and such first. So just keep that in mind. We'll eventually get there, but this is going to be at least a 3-part series in which we are kind of building up to the actual Aldol reaction. But we have to learn about enolates and all of these guys first. So enolates can react with electrophiles, and they can either react with electrophiles on the oxygen that has a negative charge, and this is called O-alkylation, right? And so the actual negative charge there that you formed can actually pick up an electrophile here, just like so, and we can form a product that now has a bond to the oxygen there. So you can see there that there is the electrophile that is now on the oxygen. Now we can look at an example of this, for instance, by using something like TMS chloride. So here's our enolate, and we're going to treat this with now an electrophile, so this can allow us to form this silyl ether. So here's our TMS chloride, and you can see that the negatively charged oxygen is going to go and attack the silicon, and we're going to kick out the chloride there, and so now we have what we call a silyl ether that has the sort of TMS there attached to it. So that's an example of ortho-alkylation, or not ortho, I'm sorry, O-alkylation. And now we're going to look at when we have carbon alkylation, whereas we're going to form a carbon-carbon bond. We're going to use those electrons that are in the double bond of your enolate to actually attack an electrophile. And that's where most of the chemistry that we're going to talk about is actually going to deal with, is actually this C alkylation here that is going to react with some electrophile in this case. So let's have a look. This requires that the electrons on negatively charged oxygen come back down, and then these guys come out and attack the electrophile that you have there. So now what we've done is we've reformed our carbonyl, and we've now made a new bond to carbon. So an example of this that we can look at here would be something like if I take this enolate from acetone that I have here and react it with, say, iodomethane. So we have now a good leaving group on there, and this is just a quick SN2 reaction. So of course you want your electrophile to be not sterically encumbered, right? And so now we formed this new carbon-carbon bond. I've extended the carbon chain here by 1 unit. I've added this CH3 to it, as you can see here, and I'll just draw CH3 to emphasize that there we've added this to our carbon chain.
Wow, I just got a big headache.
Okay, the next facet of this is that what we want to do when we're using these reactions, right, we want to make sure that we have, if we're going to form the enolate, that we're going to use a strong base that will completely form the enolate. We don't want half of it formed. We want the whole enolate formed. So one of those bases that you would use to form the enolate is called LDA, or lithium diisopropylamide, and it looks just like this, and so there's a negatively charged there. So what you can see from this is that it is a bit sterically encumbered. We have these two isopropyl groups that are around it, and so you can see that it's quite a bit bulky. This is in fact a very strong base that is used to completely or 100% enolize something that has an enolizable proton, right? So we basically take it from diisopropylamine and treat this with N-butyllithium at minus 78 degrees, and you're going to form here your diisopropylamide. And then this will then be used to form your various enolates. Another base that is quite strong that you can use to, in fact, enolize something is sodium hydride here. And so sodium hydride is, of course, also a strong base. And it's actually pretty reactive, so it's stored in sort of this oil immersion that is about 60% sodium hydride typically.
Come again?
Okay, so now what we're going to do is we're going to look here. So if we are, in fact, alkylating with this, so we're going to basically use the enolate here to attack this electrophile, like so. And let's draw the products that we have here. So there we've got our alkylated version that you can see. What you want, of course, as I was saying before, is that you want to make sure that you use at least one full equivalent of your base. So we're going to use one full equivalent of either LDA or sodium hydride of some sort, right? To make sure that we have complete enolization, right? So we don't want half enolates being formed, right? We want all of our enolizable protons to be removed so that everything forms the enolate. So if we look at sort of an example here for that, if I draw this guy here, now notice that I have only one set, because on the one side is an aromatic ring. I have only one set of enolizable protons, and they're on the right, which I just drew one out for you. And let's just say that our base in this case is LDA or sodium hydride. And here we're going to form our enolate. And we're going to make sure that we're using one full equivalent here. And we're going to completely or 100% enolize what we have. And now we're going to add this to, say, iodomethane. And this is sort of a common trend that you're going to see now, right? We're going to use these electrophiles. This iodomethane is a nice methylating reagent, and we're going to add this methyl group here to our enolate, now forming a new carbon-carbon bond that you can see. Right. In this case, though, the base, I would use a full equivalent, if not more, to make sure that I get 100% enolization at this point.
¿Cómo se llama? No, Kelly Clarkson!
Okay. Now let's look at some sort of different enolates here. Something that we need to kind of focus in on once sort of we look at this. So we have two sort of enolates that we can envision. We have the thermodynamic enolate, and then we also have the kinetic enolate, right? And so the thermodynamic enolate is the one that's going to be a bit more stable, right? And you can kind of think of this, of course, as your double bond is more highly substituted at that point, right? So that gives you the more stable enolate. So here's an example. Notice that I have this one enolizable proton here on the right, and I have two that are on the left of this ketone. and I can form the thermodynamic enolate, which is this guy that you see here, right, with a more highly substituted double bond. And we can then add something to this. So let's add a methyl group here by this bromomethane. And there, I'll just draw this in so you can see that we've added this methyl group right there to it. Right, and this is from the thermodynamic enolate, the more highly substituted double bond that is there. Right, and on the double bond is more stable. Versus the other side, that if we had where there was no methyl group on there, and you can see that that would be a less substituted double bond. The kinetic enolate, on the other hand, is the one that often can form faster. And we can ensure that we, in fact, get this, on this case, we get the kinetic enolate if I use something that's a bit bulky, right? So here is an example again. We have our same sort of situation. This time, though, I'm not going to use sodium hydride. I'm going to actually use LDA. Remember that we said LDA was quite bulky, so it can't really get in there to deprotonate the thermodynamic enolizable proton, right? So it has to go on the left side here. And so in this case now, we're going to form the kinetic enolate. It's less stable. And it also forms faster, and so we're going to alkylate in that fashion. Right, so again, just to point out here that LDA is much larger and also bulky, and so it has those two isopropyl groups that are on there. And so it can't really get in there to deprotonate the thermodynamic enolizable proton. Now, one thing that you also need to keep in mind on this as we continue our discussion here with these enolates and enols is that we also have to remember from prior chemistry that enamines and silyl ethers we can also use. So enamines, what are these guys? Well, remember, if you recall back from the sort of chemistry of carbonyls, that we can form an enamine using a secondary amine. And if we were to use a primary amine, then you would form an imine. Right, so that's something that you're going to want to make sure that you review and understand the chemistry behind those. Also remember that if you have something that is alpha beta unsaturated, that amines can also add in 1,4 addition too. So remember, don't forget about that guy as well. So remember that amines tend to add 1,4. So here's an example. So here's acetone, and we're going to treat this with our secondary amine, and lo and behold, there is our enamine. And I can use actually this enamine to alkylate. So if you envision that this nitrogen kicking its lone pairs down, right, that now give us a plus charge on the nitrogen, and we have alkylated this right there, and then we can undergo hydrolysis and go right back to our ketone. So notice that we're not using a strong base in this case, right? That we're just using the enamine formation, and we can alkylate in this fashion. This is called Stork enamine synthesis, and it is quite common to alkylate as well without the presence of strong bases. We can also use this sort of silyl ether, kind of traps our enolate there that we have. So we form this silyl ether that you see here, right? And now this guy can go off, and we can actually use this to alkylate something as well. just put a generic electrophile there for now. And in the same sort of process that we've been seeing, right, we can alkylate, and then of course we're going to get rid of the silyl ether, and so titanium tetrachloride is good for that, and so we can remove the silyl ether and go back to our carbonyl compound that has the electrophile that's been added to it there. So again, I just want to point out to you that the enamine synthesis that we have here doesn't require the use of a strong base, so we're not using either LDA or sodium hydride or anything like that
How do you feel now?
to form this. Now, aldehydes and ketones, we can actually brominate these guys, and we can do this under either acidic and or basic conditions. So if we look at acidic conditions here, we're going to use some acid to actually form our enol. So we formed the enol from this guy. And now I treat this with bromine, and it turns out that the lone pair on the oxygen can kick in, and it can actually come out and force the sort of double bond there to attack our bromine. And we can actually brominate this guy and put a bromine alpha to the carbonyl. And then finally, we're going to remove or reform our acid by removing the acidic proton that is, in fact, on the carbonyl here. And so you can have either Br minus do this or the conjugate base of the acid go back and pick this up. It's kind of all the same. So there you see that we basically get rid of that proton. Now, let's look, though, at the basic conditions for this. And I'm going to show you that something a little different here is going to happen. So we're going to form this. We have only one set of enolizable protons. All of these guys here on the right that I've drawn out. And I'm going to put base generic here for now. And so note that we're going to form the enolate. So let's draw our enolates over here now that we've formed. So now we can use this enolate here to attack a bromine and add this bromine on there. Now, one thing that I want to point out, though, that you may not consider is that think about what happens to the acidity of the hydrogens that are left. Notice that these guys are attached to a bromine that's electron withdrawing, right? And so what does that do to the acidity? Well, it increases the acidity of the remaining hydrogens. So now if I have base in solution, guess what? It's going to rapidly want to deprotonate those. And as you add another one, it becomes even more acidic, right? So it turns out that this process of the base deprotonating it the base deprotonating it happens sort of, it repeats itself until all of the alpha hydrogens there are gone. So you can see that here we have all of these bromines that are now substituted on there. And if we now convert our base to OH minus, notice that this guy is going to attack the carbonyl. And I have these bromines here that are on this carbon. And so if, in fact, now that the negatively charged oxygen comes back down, it can actually kick out this carbanion because it has all of these bromines that are on there. So it can, in fact, stabilize that negative charge, right? So here is this guy that we have now, our sort of CBr3 with a minus charge on the carbon. But that's going to quickly abstract the proton from this. And so we have, in this case, we have our formate here, and then we have the CHBr3. If that was chlorine, it would be chloroform. So that is an example of the haloform reaction. All right, so the last one for this series that we're going to talk to, or this video that we're going to talk about, is bromination of carboxylic acids at the alpha position. And we're going to do this with a reaction that we call the Hell-Volhard-Zelinsky reaction. And so it turns out that we can actually alpha brominate these carboxylic acids with a mixture of PBr3 and Br2. So if I were to draw a carboxylic acid here, and convert this to the acid bromide, so PBr3. And again, this is chemistry that you should be aware of, right? So the conversion to the acid bromide there. So now I have something that's actually really, really reactive. And I can then enolize this guy. So we form the enolates here, or enol that we have. Again, it's important to remember that we are in acidic conditions. And so this guy can kick in, and then we can do the bromination just like we've done before. And there should be a bromine on the end of that enol there.
The sooner you get back to work, the sooner you'll be partnerized. I taste shit. You do?
All right, so now we have this protonated carbonyl with the bromine there that wasn't in the last structure, but it's still there. And there we have now, we're going to remove this acidic proton that is on the carbonyl. And so if we draw our product here, you see that we have the bromine at the alpha position, and then we still have our bromine there as our acid halide. And as soon as you go to work this guy up and you add a little bit of water to it, it's going to quickly hydrolyze back to the carboxylic acid. It's super reactive there. So then we're going to quickly reform our carboxylic acid. And so this is the Helmholtz-Zielinski reaction, alpha bromination of a carboxylic acid. Hey, thanks for watching. I hope this was helpful. Stay tuned for the next one.